In this video, we'll be going through question 11 from the 2021 HSC Mathematics Extension 1 exam. This will be the third in a series of 5 videos covering the entire paper. So let's get into part A. The direction field for a differential equation is given on page 1 of the question 12 writing booklet. The graph of a particular solution to the differential equation passes through the point P. On the diagram provided in the writing booklet, sketch the graph of this particular solution. So here we have our direction field. It's been given to us. Thankfully, we don't have to draw it. But what we do need to draw is we need to draw a particular solution, and that particular solution has to pass through this point P. Now, before we get started, a couple of comments that I think I'd like to make about this is that one thing we know about differential equations and direction fields is that a slight change in your initial conditions can produce a very large change in your solution, your particular solution. And so in the context of this question, we obviously know that it has to pass through this point, but basically what happens outside of that point is not really 100% determined in the scenario of an exam. Because, for example, someone might draw it going like this, and then just a little bit below these other lines, or someone might draw it going like this. Maybe it's coming down a little bit slightly underneath it, and it might end up taking it down like this or something. So there's going to be a couple of different solutions which could be plausible or might be accepted. But the main thing that we want to make sure with a question like this is that whenever we draw our particular solution, we never cross over any of these little line segments that are drawn in for us, any of these lines. And the reason for that is because those line segments actually represent a part of a tangent at a particular solution that's at that point. And obviously the tangent isn't going to cross through the curve, the particular solution, and so it has to be tangent to the particular solution. So if I'm ever going to touch one of these lines, I can only ever touch it. I can't go through it. I can't cut through it. Okay, and that's really important. And that's a comment that the HSC markers actually made when they were giving feedback about this type of question. So let's have a go at trying to just graph this particular solution. Like I said, there could be more than one possible answer, but let's try to do our best. Okay, so something like that would be quite plausible. We can see that we don't cross over any of the lines. We're passing through this point here, even though actually probably should tidy that one up just a little bit. Okay, we're not crossing through any of our lines. We're just following along through the direction that those tangents are giving us. Okay, and that's the end of part A. Let's have a look at part B now. A bottle of water with temperature 5 degrees Celsius is placed on a table in a room. The temperature of the room remains constant at 25 degrees Celsius. After T minutes, the temperature of the water in degrees Celsius is capital T. The temperature of the water can be modeled using the differential equation dt on dt equals K times capital T minus 25, where K is the growth constant. Part I. After 8 minutes, the temperature of the water is 10 degrees Celsius. By solving the differential equation, find the value of T when the temperature of the water reaches 20 degrees Celsius, and we want to give our answer to the nearest minute. Okay, so here's our differential equation, and we've been given a lot of conditions that go along with this, a lot of other extra information. So it's important to try to write that down in a nice, succinct way to help you approach a question like this. So what are we told? We're told that the bottle of water initially has a temperature of 5 degrees. Now, they don't use the word initially, but we know it's an initial condition there because when it's placed on the table in the room, it has a temperature of 5 degrees. So I know that when lowercase t equals 0, capital T is equal to 5. And then we're told that the temperature of the room remains constant at 25 degrees. But actually, that's not that important in terms of a condition other than setting up the differential equation, which they've already done for us. So that might be a little bit of a source of confusion, but we don't know anything else other than the fact that just the room temperature is 25. That's got nothing to do with capital T, which is the temperature of the bottle. And then we're told in part I that after 8 minutes, the temperature of the water is 10 degrees. So when T is equal to 8, capital T is equal to 10. And what we want to do is we want to solve the differential equation to find what value of t, what value of lowercase t after what time is the temperature equal to 20 degrees. So this is the sort of the information we've been given, and this is what we're looking for. Okay, so we need to solve this differential equation. It's a separable differential equation, so I'm going to separate out onto the left-hand side and the right-hand side capital T, and on the other side I'm going to have lowercase t. So in doing that, I get dt on t minus 25 equals k times dt. Of course, I could have k on either side because it's a constant. I'm just going to keep it on the right-hand side. And now that I've separated out, I am able to integrate. Okay, the left-hand side, integrating this gives me log of t minus 25, but I need to be careful. I must have absolute value signs there. It's actually quite important in a question like this, and we'll see why in a moment. And then that's going to be equal to k times t, and I need a constant on either side. So I'm just going to put it on my right-hand side here, plus c. Now what I need to do is, well, I've got two constants, lowercase k and capital C, and I need two equations in order to work out those constants. And how convenient for us that we've got two bits of information which would help us set up two equations. Okay. Cool. So I'm going to use my first one here. When t is equal to 0, capital T is equal to 5. I'm going to sub that in, and I'll get the log of 5 minus 25. And here you can see why I really need to have the absolute value sign. Because if I didn't have absolute values, I would be subbing in 5 minus 25, which is negative 20, into the log function. Without the absolute values, that would break, but the absolute values make it possible. And this is going to be equal to, this will become 0, because lowercase t is 0, plus c. And so I get that c is equal to log of 20. Okay, I'm going to substitute that into my equation now. Log of t minus 25 equals kt plus log of 20. I'll probably bring it over to the other side. Log of t minus 25 minus log 20, and then I can see that I can use some log laws to combine those two logs just into one, and we get the following. Great, now I only need to work out what k is, and I can sort of tick this off, I've used it. Now I need to use this bit of information. When t is 8, capital T is 10. So when t is equal to 8, capital T is 10. Go ahead and substitute that in. Okay, so we get log of 10 minus 25 is negative 15. Negative 15 divided by 20. That's equal to k times 8. To get k by itself, I'll divide by 8. And this would simplify to negative 3/4. The absolute value makes it positive 3/4. So there's my value of k. And so I can go ahead and substitute that back into this equation, constantly updating my equation whenever I work out a bit of information. I get log of t minus 25 on 20 equals 1 on 8 log of 3/4 times t. Okay, now we want to work out what is the value of lowercase t when capital T is 20. Okay, so what I might do, actually, yeah, we'll just substitute in, doesn't really matter. No, we're substituting capital T. So when capital T is 20, we get log of 20 minus 25 on 20 equals 1 on 8 log of 3/4 times t. And then simply, we can plug all this into a calculator. I would plug that into a calculator and then divide by whatever this value is. Putting that into a calculator should give us something along the lines of 38.55. Okay, and then we want it to the nearest minute, so 39 minutes. Okay, and so that is part I done. Now for part double I, it says to sketch the graph of capital T as a function of lowercase t. So sketching temperature versus time. So in order to do that, I probably need to make, here we've got an equation which relates capital T to lowercase t, but we probably should make capital T the subject of this equation. Okay, so in order to do this, what I'm going to say is I might actually just, if I'm in an exam, I would rewrite it. I can duplicate it here. What I'm going to do is I'm going to rewrite this thing as k, and just on the side say where k is equal to blah, blah, blah. Okay, so we've got log of t minus 25 on 20 equals kt, where k equals 1 on 8 log of 3/4. The reason I'm going to do that is because I'm anticipating the fact that I'm going to have to exponentiate both sides. And putting this in the power just going to make things really cramped up. Okay. So now I'm going to do that. I'm going to exponentiate both sides. Remember that we still have these absolute values. We haven't really stripped those away yet. This is going to be e to the kt. Once again, where k is equal to that. Okay, now I'll strip them away and say t minus 25 on 20 equals plus or minus e to the kt. I'll multiply by 20, and then at the same time, I'll just add 25 to both sides. So I'm just doing 2 steps in one here. Should be okay. The reason it should be okay is because this question is only worth 1 mark, and the mark that they're looking for is the graph. Here we're just trying to get the equation, so it's obvious to us what it looks like. All right, so I've got these two equations. I've got 25 plus 20e to the kt and 25 minus 20e to the kt. And the question is, well, which one do I take? Because it's not going to be the case that they're both correct. Which one is going to be the correct one? And the way we determine that is we go back up here and we check our initial conditions to see which of those satisfies, or which equation rather satisfies, or would, let me rephrase that, which equation would make these satisfy the equation. Okay, so I'm going to just use the first one once again because it's easiest to use. It's got a 0 in it. So if I subbed in t equal to 0 and capital T equal to 25, we think about, well, we need the left-hand side to be equal to the right-hand side. So we get 25 equals 25 plus or minus 20e to the 0. 20e to the 0 is equal to 1. So this is saying 25, that should be a 5 there, my bad. So this is saying 5 equals 25 plus or minus 20. Well, obviously we have to take the negative case, which means, well, I mean, you don't even need to write this, but you can say here that clearly we take the negative. Okay, so we're going to take the negative case, and so our equation is the following: t equals 25 minus 20e to the kt. And I'm just going to write here once again, where k equals 1 on 8, the log of 3/4. And the reason that I'm really making sure to remember what k is because the shape of this dramatically changes depending on whether k is positive or negative. And in this case, we can determine, even without a calculator, that k is going to be negative, because 1 on 8 is a positive value, and then log of something in here which is less than 1 would produce a negative value. So this will be negative times this which is positive. Overall gives me a k value which is negative. Okay, so that's important because now I need to try to investigate what's happening to this graph when t goes to infinity. So I'm going to quickly draw up an axis. Okay, so I've drawn up an axis here, and I've marked off 5, 10, 15, 20, 25. And the reason I'm doing this is because I know that I start at 5, because I know when t is 0, capital T is 5. That was the initial condition. And when I set t to go to infinity, as in positive infinity, I would have a positive large number multiplied by a negative number, which overall would become a really large negative number. And then e to the power of a large negative number is essentially 0. And so 20 times 0 would be 0, and we're left with just 25. And so all that is to say that when t approaches infinity, my capital T is going to be approaching 25. And so it would look something like this when I graph it. Now, that's probably enough to get the 1 mark. It is only worth 1 mark. And I mean, all this other work that we did here, that may have already been done in part I. So it may not have been necessary for you to do this, but I needed it in order to see the equation. One other thing that we could do if we wanted to really put in all the information that we know is we did know one other condition, which was that when t was equal to 8, capital T was equal to 20. So I can substitute that in. When t equals 8, sorry, was it 20 or 10? Yeah, it was 10. When t equals 8, my time was 20. So this time should be 8 here. Like that. So we could include that if we wanted, but I think even if we didn't, the graph is enough. And that's the end of part B. Part C says, use mathematical induction to prove that 1 over 1 times 2 times 3 plus 1 over 2 times 3 times 4 plus all the way up to 1 over n times n plus 1 times n plus 2 equals a quarter minus 1 on 2 times n plus 1 times n plus 2. And we want to prove this for all integers n greater than or equal to 1. So here's the statement that we want to prove. We're using mathematical induction. In extension 1, induction always starts at n equals 1. It's written into the syllabus. So our base case now, we're going to start off with proving n equals 1 is true. So base case is n equal to 1. Now, I need to show that my left-hand side is equal to my right-hand side. So let me compute the left-hand side. The left-hand side means I start with this term, and I go up to whatever this term would be when I sub n equal to 1 in. So I'm starting at 1 on 1 times 2 times 3, and I'm going up to 1 over 1 times 2 times 3. So that means the only term is that term. This is 1 on 6. And then I do the same for the right-hand side. I sub in n equal to 1. I get a quarter minus 1 over 2 times 2 times 3. That's a quarter minus 1 on 12. This is, let's see, 3 on 12 minus a 12th, which is 2 on 12, which is 1 on 6. Okay, and so therefore the right-hand side is equal to the left-hand side, and so our base case is true. Okay, now we need to make our inductive hypothesis. So we want to assume that statement is true for n equal to k, where k is some integer greater than or equal to 1. Okay, obviously k has to take the same sort of values that n has to take. All right, let's write down what that means. So therefore, we're assuming 1 on 1 times 2 times 3 plus 1 on 2 times 3 times 4 all the way up to 1 on k times k plus 1 times k plus 2. We want to assume that that's equal to a quarter minus 1 on 2 times k plus 1 times k plus 2. And because this is my assumption, I know that I'm definitely going to have to use it later on. I'm going to call it star, because when I refer to it, I can just say by star. Okay. Now, what we want to prove is we want to prove that n equals k plus 1 is true. So we want to prove that 1 over 1 times 2 times 3 plus 1 on 2 times 3 times 4 plus all the way up to 1 over, now I have to substitute k plus 1 wherever I see a k, wherever I see an n. So that's going to be k plus 1, k plus 2, k plus 3. I want to show that that's equal to a quarter minus 1 over 2 times k plus 2, k plus 3. Okay, so I'm going to start with my left-hand side, try to make my way across to the right-hand side, and in that process, I know I have to use my assumption. Okay, so our left-hand side. We really need to write this out again. It's not appropriate to just say left-hand side equals and then start simplifying it or doing some sort of algebra. We should write it out first and then go and do the algebra. So 1 on 1 times 2 times 3, 1 on 2 times 3 times 4. I always like to write the second last term when I'm dealing with a summation. K into k plus 1 into k plus 2. And then we have our last term. K plus 1, k plus 2, k plus 3. Of course, the reason that we write the second last term is because that's actually the last term of the assumption. So everything in these pink brackets here is precisely, everything in the pink brackets here is precisely the left-hand side of my assumption. And so now I can just write that this is equal to 1/4 minus 1 on 2 times k plus 1, k plus 2. So I'm going to even put that in pink brackets so we know that that matches up with the pink brackets above. And then I've still got this term sitting on the end. So plus 1 on k plus 1, k plus 2, k plus 3. Okay, so now I'm looking at what I've currently got, and I'm comparing it to what I'm trying to work towards. And I can notice that both of them have 1/4 sitting out the front, and so I'm never going to touch that 1/4 again. That's going to stay as it is. And basically what I'm doing is now I need to work with these terms and try to turn them into this term here. Okay, so what can I see? I can see that I have one fraction. Here I've got two fractions. Let's try to make a common denominator and see what happens after that. So I've got that 1/4 that I'm never touching again. Okay, now to make a common denominator, I'd have to multiply this fraction top and bottom by k plus 3, and I'd have to multiply this fraction top and bottom by 2. So let's do that. I'd get minus k plus 3 all over 2 times k plus 1, k plus 2, k plus 3, plus 2 all over 2 times k plus 1, k plus 2, k plus 3. So now these fractions have the same denominator. I can merge them into one. And I'm actually going to write it in this order. I'm going to write plus 2 minus k plus 3 in brackets because we're subtracting the entire numerator. And all of that will be over 2 times k plus 1, k plus 2, k plus 3. Keeping in mind that what we're trying to work towards is something which has a 2, k plus 2, k plus 3 in the denominator. So here, we've got this extra factor of k plus 1. Hopefully, that will cancel out once we do our simplifications. So it's 1/4 plus 2 minus k minus 3. Actually, you could probably just write this as -1 minus k. And then I think you can maybe see that once I factor out a -1 in the top, that's going to cancel with this down here. But it's really important that with these kinds of questions where you're proving something, that you show all of those steps. You don't just jump through steps, because often you've got the result that you want to prove. And so just stating that result, it's not really worth anything. It's more about showing it. So I factor out the -1, 1 plus k, and I've got this denominator, and now I will cancel off, and I get to the result that I want. So cancelling 1 plus k with the k plus 1 gets me 1/4 minus 1 over 2 into k plus 2, k plus 3. And that is my right-hand side. And so then I can make a statement. Therefore, it's true for n equals k plus 1 if n equals k is true. And then our concluding statement, you don't have to write that essay that teachers often teach at schools. You only have to write something of the form, therefore it's true by mathematical induction. And you would want to state for what values it's true for n greater than or equal to 1. Okay, and that's the end of our induction, end of part C. Part D. A function is defined by f of x equals 4 minus brackets 1 minus x on 2 close brackets squared for x in the domain minus infinity up to 2, and we're including 2. Part I says, sketch the graph of y equals f of x showing the x and y intercepts. Okay, so here we've got our function, and I think it's clear enough to see that this is going to end up being a quadratic, and so the graph is going to be a parabola. But we've also got some sort of a restriction on the domain. Now let's just ignore the restriction for a moment and deal with this so that we can see what the general shape is going to be, if there's any key features that we can identify. Now, what I can see here is that this is almost in a very nice form, which would allow us to read off our vertex. So that form would be something like y equals a into x minus h squared plus k. So if we can turn this equation into something of this form, we'd be able to read off our vertex as being h comma k. Okay, and so that's what I'm going to try to do here, because if I can work out the vertex, that's an important feature of a parabola. The x and y intercepts are obviously going to also be important, but I'm going to try to do the vertex first because it's already almost in that form. The only thing that I can see that's different is that I need to have a single x inside of this bracket, but here I've got an x divided by 2, so I'm going to factor out a half out of the brackets. Okay, so factoring out a half, I would get 1/2 into 2 minus x, and then all of that would be squared, and so that means I have 1/4 outside of 2 minus x all squared. Okay, and then if I just write this in a slightly different order, plus 4, and in fact, whether I've got 2 minus x or x minus 2, it won't matter because it's getting squared, so I can write it like that. And you can see quite clearly now this is in the form of a times x minus h squared plus k. And so this tells me that my vertex is going to occur at 2, 4. Okay, so the vertex is there. We've got it. That's an important point for the graph of a parabola. Now we just want to find x and y intercepts. So to find at least the y-intercept is quite easy. You just sub in x equal to 0. So when x is 0, f of 0 is 4 minus 1, which is going to end up being 3. And so 3 is our y-intercept. And if I want to find my x-intercepts, I'm actually going to take this equation here, this f of x equation, which is, whoops, it's meant to be done with the laser, which is probably the better one to work with. So let's set that equal to 0, or set f of x equal to 0, I should say. If I do a couple of steps in one, x minus 2 squared equals 16. So x equals 2 plus or minus 4. Okay, and so we get -2 or 6. But of course, we look at our domain. Our domain is everything less than or equal to 2, so we would actually reject this value here. But you can see that if we weren't restricted, these would be the 2 x-intercepts of our parabola. Okay, and it might not be a bad idea to just have that in the back of your mind, just so you can orient yourself when you're drawing your parabola. So I'm going to go ahead and draw this now. Okay, and so we get something looking like this. This goes on forever in that direction. This is an endpoint here. If we didn't have a restriction, we would get some symmetry going across like that. But we do have our domain restriction. Okay, so that's the end of part I. The next part says find the equation of the inverse function f inverse of x and state its domain. Okay, so now we have to just find the equation of f inverse. So I'm going to do this part down here. We know that f of x was given by, let's go back up, 4 minus 1 minus x on 2. So I'm going to write f of x, and I'm going to replace it with y, because when I swap, I want to swap with a y. It's 4 minus 1 minus x on 2 all squared. And so if I want to get f inverse, that comes about by swapping x and y. But then I of course want to solve this for y now. But here's the problem, and it's quite a common mistake that's made, is that we typically remember that to get the inverse function, we swap the x and y roles. However, we also have to remember that our domain and range are going to swap. So our original domain was minus infinity up to 2. This has now become the range. This has become the values that y can take. So y, in my inverse, takes these values. And this is going to become really important later on when we have to determine whether we're going to take a plus or a minus. Okay, so let's do the work now in order to make y the subject. So I've got y, 1 minus y on 2 squared equals 4 minus x. square rooting both sides, and here you can see that by square rooting I'm introducing a plus or minus, and that's going to be resolved at the end using our restriction on y. Okay, y on 2 equals 1 plus or minus root 4 minus x, and multiplying everything by 2 gives me 2 plus or minus 2 root 4 minus x. Now, once again, I've got that y has to be anything less than or equal to 2. So if I've already got a 2 here, I can't add anything else that's positive. This part here is positive, so I can't be adding something onto 2, otherwise I'd be exceeding my restriction on y. So I'm going to say since y is in between minus infinity to 2, now I'm able to justify that I'm only taking the negative case here instead of the positive case. So y equals 2 minus 2 root 4 minus x, and I need to state domain and range of this. Okay, so the domain and the range. Now the range, we've already got it. The range is, that should be inclusive, minus infinity up to 2. The domain, well, you could do the domain in two ways. You could just have a look at this function and see what the domain is. But maybe another way is if you can go back up here, see what the range of f of x is, that's going to become the domain of the inverse function. So what's the range of this blue curve? The range is anything less than or equal to 4. So similarly, here our domain is going to be x basically less than or equal to 4. And you can see you could also get that by just checking that whatever's underneath your square root has to be greater than or equal to 0. And so that means x would be less than or equal to 4. Okay, so there's two ways of doing that. Great, so we've got our inverse function. I suppose I probably would also just write using the inverse function notation instead of just leaving it as y equals. I might also just write it with an inverse function notation. But that's that part. Now we just have to sketch. I believe that's what the next part says. It says sketch the graph of y equals the inverse function. So to do this, what I'm going to do is I'm actually just going to copy this down here. And I know that when I sketch my inverse function, the roles of x and y are going to swap. Okay, so here I have a point 2, 4. That point is going to be reflected across the line y equals x, and it's going to become 4, 2. So 4, 2 would sit somewhere here. I had a y-intercept of 3. That's now going to become an x-intercept of 3. I had an x-intercept of -2. That's going to now become a y-intercept of -2. Okay. Now, you may or may not be drawing this on the same graph. It's probably, I think it's a bit too much to ask you to draw on the same graph, and they haven't specifically asked you to draw on the same graph. But if you were able to, if you had the time and you wanted to show the reflective nature, it might not be a bad idea to draw in the original as well, and then draw in the line y equals x, which is something like this, to give you that symmetry across the line y equals x. Okay, and if you're drawing that in, let's just get a full line, you would write y equals x. Okay, but I think that's unnecessary, especially since it's only worth 1 mark. Cool, that's the end of question 12.